Trojans Talk Research is a monthly spotlight on the research interests of Troy's faculty, presented by Troy University's Office of Sponsored Programs. This month, Dr. Hoa Dinh introduces the concept of barycenters of data sets and explores the question of how to transform any point into a barycenter.
I'm an associate professor on the math department, and I have worked at Troy this is 7th years, and I'm originally from Vietnam. And you know, there was a very interesting story about Troy. So I did my bachelor degree and then PhD degree from Russia in 2010, and then I turned back to Vietnam. I worked for a private university in Vietnam in Da Nang city. Did you hear about Da Nang? Maybe not, that's fine. And then I met the first representative of Troy University in Vietnam. I talked to him, I learned English with him, you know. And then it turns out like, how many years later, like 8 years later, I got hired and started working at Troy. So it was very interesting story. In the past few years, I did a lot, research on barycenters, distant functions, some kind of that. So I give you some idea about, distances, right? For example, we know that, in plane, we measure distance from 2 points. Is that correct? So we have Euclidean distance. If you have coordinates of 1 point, which is like x1, y1, another one is x2, y2. So you use the distance formula from high school, which is square root of x1 minus x2 squared plus y1 minus y2 squared. And you take square root of that. So it is Euclidean distance. So we all know about that. And what is the barycenter of an interval? Do you remember the midpoint formula? That guy, he remembered me. Do you remember that? Yes. You passed that course. Anyway, just kidding. So the midpoint formula is you just take the average. Take x1 plus x2 divided by 2, and y1 plus y2 divided by 2. So that is your midpoint. Okay? Again, this is from high school. It turns out that, that formula works only for Euclidean distance, which is, I just remind you, it's called Euclidean distance. Euclidean distance is about distance between 2 points in plane. So, there's another notion which is called geodesic curve. So what does mean geodesic curve, right? For example, in plane, which one is the shortest path joining 2 points? What do you think? The shortest path connecting 2 points in the plane, what is that? Straight line, yes, that is straight line. And the midpoint is, the barycenter of those points is the center of the geodesic curve. I mentioned geodesics because, the thing is when you change the distance function, that means when you change the way you measure distances, then basically that changes everything. So you can imagine about the Earth, right? You cannot, so we have like, okay, sphere, let's say that. You pick one point from here, another point from here. You just cannot use distance, use straight line to connect them. Is that correct? Because you are working on the surface of the Earth. There's no straight line over there. Is that correct? So you need to do something else. So basically the curve you do is like this, right? Not straight line. Does that make sense? So we need a new type of measurements. That's it. And then, I think I see some guy from geometry major here. He was in my class. I think I told him about some distances, right? The way we measure, distance between 2 vectors in the surface of the Earth. Remember that? Yeah. Can you tell the audience about that? Yeah, he remember I told him something, but then that's fine. I tell you this, right? So we cannot measure, we cannot use the way to take the geodesic curve, which is straight line. You cannot pass through the Earth, right? So you have to measure, you use another distance, which is called log distance. You remember the log, right? Logarithmic functions. So instead of instead of calculating distance between x1, y1, x2, y2, you calculate the distance between log x1, log y1, log x2, and log y2. Can you imagine that? So kind of, you know, okay, I want to measure distance from x1, y1, x2, y2. So I will calculate a Euclidean distance between log x1, log y1, log x2, and log y2. Does that make sense? So the way there's some kind of geometric, property of that is, you consider some sphere like this. You pick two points on the sphere. In order to measure distance between these 2 points, I will fix some point, I will find some tangent plane. Can you imagine what is tangent plane? The tangent plane is kind of, a sphere like this, so tangent plane look like this. And then I will project 2 given points on the tangent plane. Make sense? Using the function logarithmic function. Logarithmic function is a very good one that, help you to go from this to this. Okay? And then we just use Euclidean distance to find, the distance. And we know on the plane, the shortest, the geodesic curve joining 2 points is, straight line. And so you can find the center of the straight line, the barycenter on the straight line, which is the midpoint. We use that from high school. Once you have that, and then you go back to the sphere. Make sense? So that's the way. We go from the sphere to the plane, and then we do calculation in the plane, and then we go back to the sphere. That's how we can find barycenter, and then corresponding geodesic curve in the surface of the Earth. Make sense? So that's how we can adjust the way we measure distances. So that example, I think is clear, right? It's clear. Go from here to here and then go back here. So basically, we change the distance. If we, the way, like last year, I published a papers on that. When we change the way we measure things, we measure distance, we change almost everything. We change the geometry of the space, even number line. We also change the number line, right? The geometry, how we look at number line. That means, we change the barycenter of all the interval. So last year I published a very, I would say, high school knowledge. Every high school student should understand that. They say, if you pick an interval, right, in the number line, and then you pick any point, not just a plus b over 2. You pick any point, I construct a distance. That means I show there is a measurement such that, any point become a barycenter of that interval. So that means, I can make any point become a barycenter using the way, just a new way of measurement. Make sense? So, I love that idea a lot. I share to everyone I met, even from computer science, everyone who does research in machine learning. And I tell you, the following idea is, in my opinion, is very new. But before that, I would give you some ideas about, how barycenters work in applications, okay? So, in reality, even in many sciences, when people do experiments, so each experiment, they have one outcome, is that correct? Then if they do like n experiments, they have n outcomes. But then in order to work with these outcomes, they cannot work with everyone. They need to work with the averaging. Make sense? They need to work with averaging. So that means if they have a data set, they have to find the averaging element of that data set. Okay? So the midpoint is kind of example of, representing. Make sense? Another example is very, I don't know if you observe that all the time or not. So if you look at the stock market, so you want to see the trend of the price, for example. It is a straight line, is that correct? Is it right? like this, and then, the trend of the price is a straight line. So what is straight line? Straight line, basically, you can find the straight line if you know two coefficients, like y equal to a plus bx. Is that correct? So basically, you need to know two numbers, a and b. So two numbers represents a point in the plane. How about that? Okay, who knows what is the meaning of the trend of the line? Like the trend of the data set, what is that? What is the meaning of that?
It means that they're making money.
Okay, so the trend of the data set. So that means that shows how the data set behaves. Is that correct? But actually, there is another meaning, of the straight line. Okay, I tell you this, right? The meaning of that line is if you have endpoints in plane, so a data set, right? So the straight line, which is the trend, that is the barycenter of the data set. Okay, the data set, even the straight line is barycenter in the sense that you will calculate the distance between, for example, you have the point, right? And then you have this straight line. So you see the distance between that point to the straight line in the horizontal direction. So if you have, this is the first point, the second point, you also do the same. And then you take sum of squares of those distance. You get some function, right? And the straight line, which is the trend of the data set, is the one which is the best fit, which makes the sum of squares of distance minimum. Can you imagine that? He learned about that. I know. We solve least square problems all the time, right? So basically, the line, and then you have point. And you calculate the distance from that point to line, and you take square of that. And how many points you have, you just sum them up. Take sum of squares. And then you minimize that function. And then you get the line. That means basically you find coefficients A and B. And that straight line is the solution of the least square problem. And actually, it is a straight line, but represented by two coefficients, A and B. And that point, AB, is the center of mass of that data set. Can you imagine that? So that's how center of mass, can be found. And, actually, that in many ways is center of mass is a point, and you can say center of mass is a line, the trend of that data set. Make sense? So that represents the whole. So basically, if you want to work with that data set, you just need to work with the barycenter. Is that correct? Like in physics, you have an object, a solid, object right here. You don't want to work with any point in that. You just work with the barycenter of that object. Is that correct? Okay, so that is about, barycenter. It is very important in many applications. I tell you one more thing related to distances and then related to barycenters. It's very, very obvious too. So basically, that is one of the main problems in healthcare science is what? For example, we have two groups in here, right? So I'm here. So I want to see I'm closer to this or I'm closer to this. Okay, so how can I do that? How do you know that I'm closest to this or I'm closest to this group?
Measure the distance between the two of them.
Measure the distance, yes. So basically, by logic, right, I will measure distance from me to each person in this group and find the minimum. Is that correct? And that minimum is understood as the distance from myself to this group. I do almost the same thing with this group. So basically, I have to calculate, distance from one to how many people in here. I have to do that, many times, right? But that is not good. Not good. If you have like a lot of people and a lot of, because here's the thing. For example, if I go to hospital, right, I just do blood tests. Blood tests give, a lot of parameters. So basically, I will be represented as a vector of parameters, as a vector of numbers. So whatever, right? How many, how many things you want to know about your body? So that will have vectors right there with many entries. So basically, each person can be represented as a vector. Does that make sense? So like you student, you can be represented as a vector of grades, of all subject you already took. Make sense? So the university look at you as a vector. I mean on the database, right? Because pull you out and then family and then grade of this and that so on, vectors. So and then they will analyze the results of my plot. They say, okay, this guy has some diabetes or whatever. And then of course they have basically there are two groups, with sickness or without sickness. So then they have to analyze, they have to calculate the distance. But then the thing is, I don't want to calculate the distance from my vector to any from this group or any from this group. I just want to do two calculations. I want to calculate my distance, the distance from me, and then the representing element of this group, which is the barycenter of this group. Does that make sense? And I want the distance from me to the barycenter of this group. And I see, if I'm closer to this, so that means I'm here. If I'm close to this, so basically, in reality, we need to find barycenters of data set all the time. So I have to solve the least square problems all the time for every group. Does that make sense? Yeah, so, and then the way we change is, the way I was thinking is, from the result I just told you, we want to make any point become barycenter. So that means if we can construct a distance, a measurement, that a given point is barycenter. So basically, we don't have to solve the least square problem. Make sense? Again, right? What the least square problem is? That means you have to calculate the distance. You find some elements such that the distance from the sum of square of the distance from that element to all the elements in the data set is minimum. Okay? So you have to solve that optimization problem. Does that make sense? So I don't want to do that. I want to fix some point, and then I want that point become a barycenter by constructing a distance. Does that make sense? Then what happens if that is possible? Okay, let's say that. So again, right, I consider two groups, and I'm a new member, right? I want to see if I'm close to this or this. I say, okay, I want to fix one element from this group. Okay, I construct a distance, a way of measurement, so that is a barycenter of this group. So that means basically I don't solve the least square problem. I save a half of the cost of computation. Does that make sense? Once I fix one guy in here, I will, construct a distance, the way of measurement, and then I will use that for this group. So basically, I save 50% of cost of computation. And that is a lot. I don't know if you heard about complexity of computation or not, but complexity, you can think about, if we calculate, each time we calculate the distance, that means how many operations we need to do. And according to that, how many seconds or how many minutes and how many hours we spend to find the result. That is complexity. Does that make sense? So if we work with the big data sets, maybe we spend a lot of time for that. So saving 50% of the cost of computation, it is a huge save. So I still could not solve that problem. I can solve that problem in plan, like if you have any, okay, let's say any, you take triangle, any figure, let's say that, in plan. Then you pick any point from that. I can construct a distance so that that point becomes a barycenter of, of that figure. But then, in machine learning, and as I say, in healthcare science or something else similar, even in quantum information theory. So basically, the data are saved, in the form of matrices. Who knows about matrices? Okay, just why don't you raise your hand? You know that, you learned that. So matrices, there's some kind of array of numbers, right? Like this. You watch the film Matrix. It's kind of that number. So basically, data are safe in the form of matrices. So working with matrices are much more complicated than with points and vectors. Much more complicated. We need to, compute a lot. So from the plan, from vectors to matrices, there, like, it's still far. But, I think that, if I can make it, so that would be very nice. And the philosophy of that is, usually people do computation for barycenters of data sets if they already given the distance. Now we think a little bit, in the reverse way. Make sense? So now we construct the distance, such as some element become barycenter, and then we apply that distance for another one. So this is a kind of not traditional way of thinking. Yeah, that is about barycenters and some applications. Do you have any questions for me? Is it clear or not? Is it good? Okay. Do you have any questions? Before I move to another part, which is kind of more philosophical. No? Okay. Yeah. So I think I still have time, so I want to share this with you. It's a little bit, philosophical or point of view. So I don't know. It's okay to share here about Buddhism, about what is barycenter in Buddhism? Who heard about that? Barycenter in Buddhism.
Your mind?
Hmm?
Your mind?
Yes, mind. And actually that is not something fancy, something difficult. It happens with every one of us every day. Okay, I tell you the situation, right? Maybe like, I have a difficulty, something, in life. And if I think that, oh my goodness, that problem is so bad to me and that maybe something happened after that as a consequence and so on, right? I will get stressful very fast. And just, I lose my balance. So you think about balance. Barycenter is balance. When I hunt for a job, one of the most asked question is, how do you balance between research and teaching, or balance between academic life and then your life? So basically, if you look at you as an element in this world, right? So basically, what do we need to do to be happy? We need to find the barycenter of us. Is that correct? So if we are in our barycenter, we are good. We feel good about that. Make sense? So, you can think about, so it really depends on how you look at things happening around you. In Buddhism, they say, okay, everything's happened, then that it will go really fast, go away. You don't have to take care. Okay, of course you have to take care about that. But if you think too much about that, you just more stressful. Okay, what does it mean you think too much about that? That means you far away from your barycenter. Make sense? So you can see, I don't know, if you play the game like this, like in the wheel, right? And then they rotate that fast. How to become better in that game? In my case, I just look at the center. So if you close your eye, right? Or you look at the center where you have, the center of the wheel. You will not feel bad. But if you look around, you feel really bad about that. Did you try that? Did you experience that? So when you look at the center of the wheel, you feel better. So basically, that is how, if we look at, if we look at the barycenter, and if we are closer to the barycenter, we will feel better, we feel happier in this life. So that is my point. Okay, go back to my theorem, right? You have interval, you can make any point become barycenter. So basically, that depends on the way you measure things. You measure the distance, let's say that. And then, when something happens around you, it is bad or not bad. It depends on how you look at this. Is that correct? How you look at that things. Is that correct? How you measure. Does that make sense? So if you think that, okay, it's okay. So then you are closer to barycenter. You look at that, okay, I'm in there. It's okay, no problem. I feel bad. I feel better with that. But if you think like, okay. One more example about that, about barycenter is, when I was thinking about barycenter, I was thinking about, which is called diversity. So, when I came to the US, like almost 10 years ago, again, with job hunting, one of the statements, which is very difficult to write, is diversity statement. I need to learn diversity of America. I need to learn, the culture and what was diversity. It was difficult, very difficult for me. And at that time, I didn't use internet that much, so to learn and the language barrier and everything else. And then, like recently, with that theorem, with the barycenter, when I think about the barycenter of myself and then of some system, right? So then I think, okay, so basically, if you look at me and someone else, like 2 points in that interval, so I can make myself, I can make the point where I am, right, become the barycenter of myself, and the other person also can make that point, the point where he is, become his barycenter. So basically, this is his barycenter, this is my barycenter. So this is his point of view, this is my point of view, basically. So basically, if I look at him and I'm jealous, it's okay, not good. I will feel bad about my life. Make sense? So that's how I can look at these things, kind of, from the point of view of mathematics, but then go back to, okay, so that means if something happened or if some people think about this, about that in different ways, okay, that's good. That is their barycenters. That is not my barycenter. I'm okay with that. I respect that. So I think that is just of my new understanding about diversity. Oh, by the way, yeah, unfortunately, a part of my presentation is about I want to share with you, some activities, some research activities I have done in the past, even from the day I joined Troy. So I travel, like in the past 2 years, I travel a lot. I used to travel a lot before I joined Troy. But then after that, I organized international conference, international seminar. We call it the Trojan math seminar. And some of my students also joined that, right? I mean, we invited several speakers, several mathematicians from all over the world. And that's how, I can promote Troy and then create a research groups in with this. And I also organize international workshops in Vietnam, in Japan. And yeah, I was visiting Japan last year twice, and this year, next year also I will twice. I like give talk and then share about barycenters and applications, especially in quantum information theory. And in March next year, I will organize a small workshop here. And we have people from Nevada, from Japan, from Korea, from Florida, Auburn University. So yeah, about 10 people come here and then discuss mathematics. And again, barycenter, divergence, distances, something like that. So yeah, thank you for listening.
Trojans Talk Research is a monthly spotlight on the research interests of choice faculty presented by Troy University's Office of Sponsored Programs.